I handle user questions, and I implement new features for teams at Meta using systemd. We've been using systemd at Meta since we adopted CentOS 7. Currently, we're at CentOS Stream 9 and moving to 10 this year somewhere. And at Meta, we use systemd everywhere. So we use it on the bare metal, of course, by virtue of using CentOS Stream. We also use it in our containers. So we don't use Podman, Docker, or similar to run our containers. We have our own container runtime, and we run these sort of system containers. So we start systemd inside of them, and then systemd starts whatever workload needs to run in that container. So systemd also runs in our containers. And we're now also doing some stuff with VMs. And of course, those VMs also run CentOS Stream. And by virtue of that, they also run systemd. We don't run systemd directly from CentOS. So we do our own backport of it so that we can adopt newer features quicker than they would appear in CentOS Stream. So we've also gradually increased our community involvement in systemd. So as I said, I'm a systemd maintainer. We have regular meetups with the rest of the systemd maintainers. And where this used to be like a yearly meetup at DevConf, now we have like these bi-weekly meetups where we chat on new topics, right? Answer complicated questions and so forth. So we're currently on systemd 2.5.7 at Meta, so the latest. We came from 2.5.5. 2.5.6 was too complicated to deploy. We didn't manage to succeed there, so we just went to 2.5.7 immediately. So what exactly do we use of systemd at Meta? Because systemd, of course, is a massive project. There's tons of tools. We don't use all of them. We use bit1, of course, because you can't use the rest without bit1. Yay, Unix philosophy. Networkd, udfd, lognd, and spawn. So networkd is pretty recent. We used to use network scripts or whatever it was called to set up network interfaces. But then a few years ago, we migrated everything to networkd. This is one place where our systemd build differs from the CentOS one, because CentOS disables networkd, but we prefer it over network manager. So we enable it and we switched everything to networkd. The rest are, well, udfd and lognd. You can't really use systemd without those. And then nspawn, we have some weird use cases where we need to run a container that can be run using our internal container runtime. And for these use cases, we tend to use nspawn because it's good enough to run something inside with some sandbox. And then, of course, unified kernel images is also something we recently switched to. Not necessarily for the security benefits of it, but more because of the ease of deployment, right? You get everything bundled into one nice package that you just copy to the ESP, which makes deployment of new kernels and initrds, microcode, and all that stuff easier. What about systemd journald? I didn't really list it on that list of things we use. So we use journald because, again, you can't use systemd without journald, but we use it very minimally. We basically have it set up to store absolutely nothing and just forward everything to syslog. Why is that the case? Journald implies a lot of extra metadata per log message. I did the math on it once, and like 70 megabytes of raw text logs will translate to about 700 megabytes of journal logs. So it's a huge well, that was before I fixed a bunch of things in systemd. It's now about at least half of that, but it still implies quite a bit of extra or write amplification for log messages. And we have a lot of internal services that log an insane amount of log messages. So that makes enabling journald persistent logging a complicated task. So we want to enable it because the journal is very useful, right? Journal codel is so much better than tailing through a random file in varlog somewhere. So we're planning to add more metrics so we can figure out which services are actually logging too much, so we can go talk to them, ask them to log a little bit less. We're also going to play around with systemd log namespaces so that we can have different journald daemons for different services, so that we can have all the internal services log to a journal namespace that doesn't persist anything, right? It just forwards to syslog. And then we can use the main journald namespace for the services which we do care about, like systemd itself, systemd networkd, dbus broker, all those core daemons that don't log too much, but whose log messages are very important to be able to debug stuff. How exactly do we do development at Meta? So we have it's similar to what we do to what our kernel team does, right? We have an upstream first policy. So we don't generally run stuff in prod that hasn't been accepted or reviewed upstream. This is especially important for anything that exposes a public API, because if we deploy something internally that changes, modifies, or adds a new public API, and then we go to upstream, ask them, can you merge this? And they say, no, this needs to be changed. Then we need to, then we're on the hook for migrating all customers using that new public API to whatever upstream decides should be the proper API for it. And that would be a lot of work for us. So we absolutely want to avoid that. And that's why we make sure that upstream is on board with everything we add to systemd. We might backport it to all the releases to make it available earlier, but we always still try to get it reviewed and accepted upstream first. So how does systemd get from the upstream at GitHub into Meta? Well, to explain that, we first need to have a look at how anything, right, any RPM, any software gets from upstream into Meta. So it always starts at Fedora. Generally, right, everything we run is packaged in Fedora. We don't run stuff from Fedora directly, so it goes into CentOS Stream every X years. What is it, 3? That we then deploy internally, right? We don't run that Red Hat Enterprise Linux directly. We run CentOS Stream. Of course, whatever is packaged in CentOS Stream definitely isn't enough for all the weird things we do at Meta. So we have a bunch of stuff in Appel as well, extra packages for Enterprise Linux. We also import internally and can be installed in where necessary. And then for the stuff that can't go in Appel, so Appel is all extras, right? Stuff that isn't in CentOS Stream. But sometimes we need to modify stuff that is in CentOS Stream. For example, systemd, right? Systemd is also shipped in RHEL, so it can't go into, or in CentOS Stream, so it can't go into Appel. So for that, we have what's called a special interest group, the Hyperscale Special Interest Group. And that's where we can handle all the stuff that can't go into Appel, basically. And the systemd backport is one example there. This then all goes to our internal mirrors and then gets installed on our hosts, containers, VMs, whatever. That's the generic overview. Then what specifically do we do for systemd? So we use we have our own fork of the systemd rawhide spec, RPM spec, which comes from Fedora. So we use the rawhide spec generally. We try to keep the diff with it as small as possible, right? So every major release, I go through our changes from the Fedora spec and try to remove as many of them as possible. So there are some differences, but currently they're very, very minimal. There are backports, both in Fedora and, of course, in our own RPM spec from upstream, right? These are just general RPM patches, nothing special there. And so something we recently added is CI. So this was sorely missing before and sorely needed to have some CI when we make changes to the RPM spec. So this year we switched to the CentOS GitLab namespace. So CentOS provides a GitLab namespace that can be used for hosting special interest group repositories, right? And with GitLab, of course, we get the GitLab CI as well. So we get the GitLab pipelines, and that gives us a lot of flexibility to add workflows that can be used to test systemd, right? So generally how this works is we build the RPMs with CBS, the CentOS Community Build System. It gives us back a set of RPMs. Then we use Fedora's testing farm project to get access to bare metal machines. And then we run the systemd integration tests against these RPMs built by CBS. So testing farm is crucial here because it gives us access to these bare metal runners, right? The systemd integration tests need to run virtualized. There is stuff, systemd runs in a container, so you can test stuff in a container, but there is a bunch of stuff like systemd UDEV is a good one, networkd also, that just isn't possible to test fully from a container. So you need to boot in a virtual machine to be able to test that properly. So that's why we need testing farm. We would like to use just the regular GitLab runners, to do this testing, but the regular GitLab hosted runners for their pipelines do not give you nested virtualization, which means that running VMs in them is extremely slow. So that's why we use testing for them. We don't really care the platform that runs the tests. We just need something that can do nested virtualization so that these tests can run in a reasonable amount of time. How does this work? That's just a glue script that downloads the RPMs, then plugs it into the system, the integration test infrastructure, and runs the tests. Once all the testing is done, the RPMs are published, are tagged, and then they get published to the CentOS Stream mirrors in the 6 specific repositories, so specifically for the Hyperscale SIG. And then we pull them into our internal mirrors to deploy them. By the way, if anyone has questions, feel free to raise your hand during the presentation. You don't need to wait for the end, and I'll be happy to answer them. So the CI/CD, how does that work? We need to bump the version, so the RPM release to the next one. If we're just doing a minor release instead of a major one, we need to update the sources. So there's a sources file shipped with every RPM. We need to update that with the hash of the new tarball. We need to do the actual build in CBS, the tests in testing form, and then publishing to the RPM repositories. And then we have 2 extra things that are like a bit custom that we came up with while developing this. So whenever we publish a new release, we also publish a git tag to the RPM repository with the RPM version as a name. And this allows us to very easily look up the exact list of comments associated with a specific RPM release. This is very useful when we need to look up later, like we have this release running in prod, exactly which comments are in there, which changes are in there, and this helps immensely with debugging stuff. That's for the RPM repository, but of course, the system that we release does not just consist of the RPM, it also consists of the upstream sources from GitHub, plus the patches that are applied by RPM. So for this, we have the unpacking step, and what this basically does is it takes the sources we get from upstream, from GitHub, plus the patches that we apply in the RPM spec, and it makes that into one Git branch, and it pushes that to an external Git repository, also in GitLab. And this again, this is also a Git tag, also named after the RPM. And the idea is the same. You can go look up that Git tag and get an exact list of commits that are in this current system release. And that is also important for debugging, right? External teams have asked us to add this because we've been doing a lot of development with systemd, right? Adding new features, and customers try to use these, and then they find out something isn't exactly working like they expected to, and they ask like, is this patch in there, or has this patch been backported? And until now, we weren't able to answer those questions because the binary RPM doesn't directly provide information on which patches are in there, right? So we really had no clue. And with this unpacked or exploded Git repository, we can now easily answer that question because we just look up the RPM version, we go to the list of comments, and we know what's in there. That's the list of tests that runs on every trigger. So we have 3. When we do an official release that we're going to deploy across the entire fleet at Meta, we just trigger a manual release build. And then, of course, on merge requests, we run a part of the pipeline. So we still run all the tests, of course. We build RPMs, we test them in testing form, and then we stop the process, right? There's no need to publish in that case. We just want to run the test. And then there's the nightly build. So this is also internal customers really want to be able to test their stuff against the very, very latest from systemd. So basically building off Git main, and we added nightly builds for that. So that runs daily, or nightly. It will just take whatever is on Git main, disregard patches or most patches, and it will build it. It will publish it to a special Hyperscale repository, and then it'll get pulled into a custom RPM repository internally, and that is made available to containers, to bare metal, right? People can opt in there, and then they can run their, of course, these aren't production environments. These are mainly testing environments, so that people can run tests and make sure their stuff doesn't break when the next version of systemd is rolled out. Testing for backing. So let's take a closer look at what exactly we contribute to both Fedora and the Fedora systemd spec and upstream. So for Fedora, the main stuff I've been doing has been adding CI there as well. So I discussed the CI in GitLab that we have for our own spec. But of course, we also want CI on every change that goes into Fedora spec, because Fedora spec is the upstream for our own. So we want to catch issues when merge requests are made to the Fedora spec instead of having to wait until we import it for the CI to run. So this is basically the same as what runs on GitLab. It also uses testing form, uses the same script, just with a different integration point. Instead of getting the RPMs from CVS, we get the RPMs from Koji. Same tests run. So not much different there. Then we have write a lot of this upstreaming to make sure that our spec in Hyperscale looks similar or the same as the Fedora spec. So this mostly comes down to adding a bunch of if conditions on if Fedora, if CentOS Stream 9, if CentOS Stream 10, gate out dependencies. It's mostly that, right? Some dependencies aren't available in CentOS Stream, some are only available on a specific version, some are only available in Fedora. So we gate those out where needed. And then, yeah, we can build from a specific upstream branch or commit. And then one other thing I added is to make sure the VM Linux SSH was for some BPF stuff, to make sure that we build from some known version of that header instead of generating it on demand from the running kernel, and various small cleanups and fixes. Oh, and then I pressed the wrong button. What have we done in systemd itself? So one project we've been working on is revamping our container runtime to be less internal, right, and use more upstream stuff. So currently, let's say we have our own version of systemd nspawn, more or less. The thing which sets up the Linux namespaces, does all the bind mounts, and then whatever required to set up a container environment and then run a workload in it. We basically want to get rid of it. We looked at systemd nspawn. The problem with systemd nspawn is that it only exposes a CLI interface. This is not great for starting containers via a machine interface, right? Via a script, via a program, via a service. You don't want to use a CLI interface to start containers there. We looked at adding a varlink interface or something similar to systemd nspawn, but systemd nspawn is very opinionated, so we decided against that. And instead, we looked at systemd service units, right? So systemd already has a bunch of sandboxing options to set up a sandbox for your service to run in. It just didn't yet expose the knobs to allow running a container in it. The specific two knobs which were missing were the bit namespace and the cgroup namespace. So we added those two. And that was more or less sufficient to be able to start systemd in a systemd service. So we're basically like think of Inception, right? We're running systemd in systemd, and this allows you to run something equivalent to a systemd nspawn container, but directly from a systemd service unit. Yeah.
Any sort of guidance setting that up, or is that a bit meta?
So the question was, if we have any documentation or whatever on how to set that up. So no documentation yet, but we did very recently land an integration test in systemd, which sets up a basic container and runs it to show how that works. If you want more information, I can give you a link to the specific test and everything later. I'm planning to extend this with to use more features and everything to make it a more representative test of what we're trying to do internally. Some other things that were necessary to add is delegate namespaces. So this is pretty technical, but when you're unsharing namespaces in Linux, the order in which you unshare them matters. Specifically, when you unshare the user namespace, which is crucial for a container, matters. So if you unshare it last or if you unshare it first is basically depends the ownership that the workload has over the other namespaces. This is best explained by an example. If you first unshare the user namespace and then unshare the mount namespace, then your workload is going to be able to do its own mounts. If you do the opposite, if you first unshare the mount namespace and then unshare the user namespace, then if you try to do a mount inside the workload, you will get a permission denied. So having control over that is also important for running containers in service units. So we added delegate namespaces, which allows you to control that. You can set it to yes or no or a specific list of namespaces to have a granular control over which namespaces are delegated to the workload and which are not. We're going to add support for mounting the BPF file system because we have a lot of workloads that need to do BPF from a container. So we're going to use BPF token to give them the permissions to do that. And then some extra options for the user namespacing to make a specific set of users available to the container via UID mapping. What else have we been doing? This is more like internal work. So I spent some time speeding up the builds. So this was basically a huge amount of menial work to remove unused includes, right? Systemd is C. It includes header files to like that. This is how C works. Over time, a lot of those headers or those includes become unused because refactoring or whatever is going on. So I think in the end, I ended up removing about 3,000 lines of code, and it was just removing headers that were not actually used by the files including them. I also made sure we didn't compile some stuff, or some stuff we were compiling like, in the worst case, we were compiling source files more than 10 times. Exact same command line every time, just doing it 10 times for absolutely no reason. So I removed all of that, and I think, and speedup was like 33%, which is always nice, right? Some CIs were made 50% faster, 40 minutes to 20 minutes. So yeah, that's just general cleanup work. We also do a lot of that at Meta just to make systemd development nicer in general, and hopefully get more contributors that think contributing to systemd is a great experience. And then the final thing, or not the final thing for this slide is varlink. So varlink is this new protocol that Leonard has decided will replace or will augment dbus in systemd. We're very interested in it at Meta because dbus is rather painful to use, right? You have to deal with dbus's type system. People that are not familiar with systemd or the Linux desktop space generally have no clue about dbus. They're also not very interested in learning it, which is completely understandable. They want to use something that they already know. So varlink is a lot better here because the interface is basically just JSON. So you send a JSON object of arguments to a method call, and you get back a JSON object, which you just parse using whatever JSON library you want. The bar is a lot lower there for using systemd's IPC interface. So we're busy adding lots of varlink interfaces to all of systemd's daemons so that our customers can use the varlink instead of dbus to interact with systemd. We've already added a varlink interface to systemd machined, and we're busy with PID1. PID1, of course, is extremely expansive when it comes to its dbus interface, so this is taking a lot of work. But we're trying to work through it. What else have we done? So we made it possible to run the integration tests from distribution packages. So we now package everything in at least in Fedora and already in Debian. Also in Arch, I think SUSE is almost there. We package everything required to be able to run the integration tests from the packages. And this is useful for running the integration tests from RPMs or depths or whatever built in the distribution's build systems. So this helps with if you can run the integration tests not just when you're building systemd from source yourself using Meson. You can also build actual RPM packages and then run the tests against those. And we needed this for our CI/CD in GitLab because we want to be testing the stuff we're going to be running in production, not some random thing we compile just to run the tests. Usually the two are similar enough that the results are the same, but depending on compilation flags or whatever that are used by the distribution, they could be different. And so we want to make sure that we're testing what we're running in prod and not some random thing we compile ourselves. We did micro, yeah, some other stuff. I guess what's interesting to mention is that just before that XC vulnerability in SSH was disclosed, we added a DL open for compression libraries in libsystemd. And that actually would have caused that vulnerability to not be exploitable because we would have never loaded the XZ library in the first place. So it's an open question whether like they tried to exploit that vulnerability quicker because we added that or not. Because as soon as this would have gotten deployed, the vulnerability wouldn't have been exploitable anymore. But I guess we'll never know. What are we going to do in the near future? More varling. We're going to make the log namespace option. We're going to re-implement it using BPF. Currently, it's not re-implemented, but like have an additional mode that implements it using BPF instead of mount namespaces. Because you can't, we want to enable this for all of Meta's internal services. You can't just run every service in a mount namespace, because then if they do a mount from the service, it won't appear anymore in the host name, in the initial mount namespace. And that can break a lot of stuff. So we're going to try and do it with BPF to make it less intrusive, so that we can just roll it out for everything without having to worry too much about the implications of it. And then we're going to, yeah, I had a really tough time with debugging dbus Roger this week, so I'm also going to see if I can make dbus more introspectable so that I'm not going to be in so much pain the next time I have to debug dbus. How do we deploy systemd at Meta? I'll go over this a bit quickly. So we basically deploy it in percentages across the fleet. We don't do everything at once. It's 1%, 5%, 10%, and so forth, until eventually the entire thing is rolled out. We mostly rely on teams telling us that something is wrong, because systemd's feature surface is so big that it's impossible to add automated alerting for everything that's using it to get reliable signal out of it. So we want to add more signal. We want to add canary tiers and everything so that we can have specific customers test something before we roll it out, but we still catch a lot of things during the rollout. So when we catch something during the rollout, what we do depends on how far we are. If we're just at 1 or 5%, it's no problem. We just roll back to release, fix the bug, and try again later. If we're already at like 75%, that's a lot of machines to roll back quickly, and like it's a pretty massive operation to roll back at that point. So we do have some automation where we can basically say, if we know only a specific set of machines is affected by the bug, we can say, keep these machines to the old version, and then we just continue with the rollout for the rest of the machines. And then once the rollout is done, again, we fix the bug, and then we remove the pinning for the specific set of machines that experience the bug, and then we also have everything on the new version. How do we debug something? We have some automation to very quickly build RPMs from source. So that enables printf debugging, right? You add new log statements, build new version, deploy it on a host where you can reproduce the issue, add and repeat until you figure out what it is, fix the bug, and you're done. So that's the very easy part. If you can't reproduce it, then you just suffer a lot. You'll try and figure out a way to capture logs, but like we said, we don't run internally. So either you could digging through syslog files, or you enable systemd journald for specific hosts and hope that all the noise from the internal services doesn't drown out the logs that you're actually interested in. So not great, and this is something we want to spend time improving in the near future. For example, by using the log namespaces. Quickly, some bugs that are interesting or funny. I'm going to skip that one because I don't have a lot of time. This is the latest one that we encountered during the 2.5.7 release. When we were rebooting some switches that were running systemd, some static default route was getting removed. This was reproducible, so I could use the easy route of just printf debugging until I found what it was. And we found eventually by adding debug logs and staring at code that some compare function wasn't using some mask to compare things, where it was using that mask in other places in the code, so that looked very suspicious. Matteo wrote an integration test for it. I rolled back the fix, and we verified it works. So we got lucky there, I guess. I still need to write a proper integration test for this specifically, but well, there's a lot to do. Another thing we found is systemd running built in CBS was running fine. All the integration tests were passing, but then when we installed it on our local service, we were getting segmentation faults when trying to start systemd. This was because of a backwards incompatible change in libbpf, which they fixed in point releases. So by the time we encountered this, like 1.4.7 was already released or something like that, and that had to fix. The problem was that CentOS Stream only had 1.4.0 and hadn't been updating to the regular patch releases. So we still only had 1.4 internally. CentOS Stream had 1.5, so they were just going from 1.4 to 1.5 to 1.6. So 1.5 was in CentOS, everything worked fine. 1.4 was in beta, we got a crash. So this is something we also need to look into fixing to make sure that whatever we're running internally shouldn't deviate too much from what CentOS Stream is, because otherwise we start running into stuff like this. Yeah, that was just fixed by making sure that the newer version of libbpf is installed when we install the new systemd release. Sometimes the bugs are extremely simple, right? You can see the if condition, standard input FD, standard output FD. Oh no, standard output FD again when it should have been standard error FD. That caused a file descriptor leak, so we got some team opening a chat with us, right? We're seeing these thousands of leaked file descriptors on our systems. And yeah, this was, I don't think I actually debugged this. I just stared really hard at the code and eventually noticed that we were using standard output FD 2 times. So yeah, Leonard wrote that code, not me. This is another one that we recently, I think this was 255. We have a hash map implementation in systemd. We iterate over it, but like most hash map implementations in various programming languages, we don't support modifying hash maps while you're iterating over it. We forget this fact quite a bit, and you get the most undebuggable crashes imaginable. So this was like also a lot of pain, a lot of staring at code. I don't think I ever debugged this properly on a host. I just went through commits, eventually found like the commit that changed this. Noticed we were modifying the hash map while iterating over it. And luckily, like rework things to not do that. We recently had another crash in PID1, which was the exact same issue. So we probably need to do something with the hash map to avoid these errors at like test time somehow, because this is extremely gnarly to debug when it happens. And unfortunately, it happens quite a bit. I'm going to skip this because I don't have time and it's a bit complicated. So if there are any more questions, I think we have time for one or two. And thanks for listening.
I kind of missed, am I audible? I kind of missed the part where you were talking about how you derive from CentOS Stream and the whole, that there was a slide about it.
This one.
Yeah. So what's your spec file closest to? Which, because I see CentOS Stream and I also see Fedora. So what's your
our RPM
meta spec file closest to?
It's almost a carbon copy of the Fedora Rawhide one.
Rawhide,
yeah.
Okay. But it makes it to a CentOS SIG repository.
Yes.
I see, okay, thank you.
I'm interested in the bootloaders, so I was just curious, you didn't mention systemd boot, so I was wondering if whether or not, what bootloader you use. Since you mentioned UKIs, I'm curious if you only care about UEFI, and finally, do you care about secure boot?
We don't care about secure boot. That's pretty simple, and then we use, David will know this better than me. We use grub on some things, but maybe we can get the mic to.
Like many things, this does not have a simple answer. On parts of the fleet, we just use grub. On parts of the fleet, on the majority of the fleet, I would say we use a custom bootloader that's built on systemd stub. I would say, I think all of the fleet is UEFI these days. I don't think we have any non-UEFI stuff left. As I mentioned, we don't care about secure boot in any way, shape, or form. We do occasionally care about doing attestation depending on how the wind is blowing. I don't think we do right now, but that might change. So things are built in a way that you could do attestation if you wanted to.
So you spoke about an unpacked repository, or so is it like equivalent to the? It's not the dist kit. It's not the repository which contains the packaging information, but rather the repository containing the systemd sources.
Right. Think of it as a copy of the upstream repository, but with the patches from the RPM applied. So we make a branch of the whatever systemd branch or comment to we're building the release from. We add all the patches from RPM on top, and then we push that as a Git tag to some repository on GitLab. And this is read-only, like this is purely for being able to introspect later which commits are running in this RPM.
Do you use some tooling to
We wrote our own thing to do this.
Okay.
We are interested in making this more reusable for others. I think Neil called it basically a reverse dist git or source git, reverse source git, right? So yeah, we think this is useful. So if others are interested, we might try to collaborate with Packet to get this more in a reusable form somewhere, so that it can be useful for more than just us.
So I'm in the team that maintains glibc for Fedora, and we use a reversed but internal unpublished version of it. We do some like patch wrangling inside the internal source repository, and then we generate the patch file and the spec file changes from it. So it was interesting that you do it like the other way.
We do it the other way around. So the reason we do it this way is that it's much easier to gate the patches which should be on this version, right? So we did it the other way around first, so kind of like you did. But the problem is that when you want to add a backport or something, you first have to go to the source git repository to make a PR there, to get it in there, and so you should run CI there, and then whatever. Then that gets merged. Then you have to go to the RPM repository, update that to pull in the new version. So you have to run CI there again. So we kind of thought this is a lot of CI running when we could just do it the opposite way and save ourselves that one step of having to modify the source git repository.
Okay.
That's the reasoning that went behind it. We can discuss offline.